Start recording. All right, so just kind of start out talking about the exam. Uh, Scores weren't great. I knew there'd be kind of usually the average is a little bit lower on this exam, and there's kind of this hiccup of transitioning to online. And the one thing I will say is I can see the views on YouTube as well as when I'm live streaming, and especially when I look at YouTube. Between my two sections, there's about 80 of you, and I'm seeing like a little bit less than 40 people watching them. Like I know maybe you think you don't need to, maybe it's hard to focus, but I got to tell you guys, I think that the rest of the semester is going to go really tough for a lot of you if you don't start watching those lectures. Um, and maybe I'm not, I'm trusting the view count that I see. Maybe some of you are somehow watching it, and I'm not getting the accurate number, but I think there's probably a strong or high number of people because I get high views on the Excel tutorial, probably because you're trying to do Excel homework, and I had higher views on the exam reviews, but I didn't have as high views on the lectures. So if you try to cram and watch these exam reviews and you try to, just try to watch the Excels for doing the homework, you're missing a large piece of the puzzle. So I highly suggest like start to watch these lectures. I'm probably, talking to myself here, but it's really, really beneficial for you guys to have that complete picture so you're not just trying to cram and get these homeworks in this exam done. Because otherwise I think we're going to have a repeat on the final if people don't start watching these. Right, so on this time I can maybe offer a little bit of extra points on that second exam. The final class is over there, right? And so on this one, what I'll do is I put, and let's see, I'll switch here. There is a extra credit assignment that is up on Blackboard right now. So where is it? Here it is. And it's worth 15 points towards your exam number 2 grade, right? So you can earn up to 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 points from getting correct answers to this. So it's basically 2 hypothesis testing problems, because that's where I think a lot of people had a tough time on this exam. I didn't know it's a tougher material, but we're going to be doing more hypothesis testing, so we need to make sure that we understand it. All right, so not only is this a way to earn back points on your exam, but it's also a way to make sure that you're understanding how we do this hypothesis testing. I did want to point out on the second question, on C, there's kind of this thing where you have to find the range. I said I wouldn't require that on the exam. So this second question is not required to earn the point for getting this question correct, but it is something that moving forward we might want to know how to do. So I just put it in there so kind of this is another review material basically. So I said it's worth 15. Basically, if you turn this in and you've just at least answered these questions, I will give you 5 points for just turning the assignment in. Right? So 5 points back in the exam for just turning this assignment in, and then a total of 10 points if you do it correctly. Okay? Any kind of grading for partial credit along the way. Right? So I highly suggest everyone do that. The reason why I offer that many points is because I believe it will then get the average of that second exam to be about where I want it to be. So just above, I think, like a 75 if everybody does that assignment and gets most of the 15 points. Okay? So please, that is due by the end of this week. So that means you need to finish it by the end of the day Friday, turn it in, upload it to Canvas by 11:59. Okay? I will make the second exam and the answers available so that you can kind of go back, look at that, see which ones you got wrong. I think as of right now I had it set so you couldn't see what the correct answers were, things like that, because you were all taking it at different times. So I'll make sure you can view those, view the correct answers, and then if you have any questions, I want you to ask me. I want everyone to get these 15 points. So I want to be there as a resource. I will be very helpful. Whether that's email, we can set up a time to meet on WebEx, Skype, Zoom, whichever app or whatever program or platform you prefer. I'll be available this week to do so. Okay? All right. Let's see. So if I go here, that's not what I want. I want to be in my primary monitor. All right. So that's kind of mentioning the exam. Like I said, the average was fairly low, a little bit lower than it usually is, probably about 5 points lower. And so this is a good way to earn back some of those points. So this week we'll kind of start, and we're going to continue to do hypothesis testing. So we're going to complicate what we've already done. So if you didn't really understand hypothesis testing before, this extra credit assignment is a great way to start to understand it, but also, it's going to be beneficial for the material that we're doing moving forward. So if we remember, we had two approaches. The p-value approach, which was we have to figure out our null alternative hypothesis. Right? Once we do that, we know if it's a left tail, right tail, two-tail test. We need to specify the level of alpha that we want to test against. Is it the 10, 5, 1% level? So alpha is of 0.1, 0.05, and 0.01. Calculate our test statistic. Once we have a test statistic, we could find the p-value, or the probability that we saw that test statistic or something more extreme. Right? So for a right-tailed test, it was the area to the right of the test statistic. Left-tailed test, area to the left. Two-tailed test, it depended on the sign of our test statistic. Right? So that's why I said more extreme. So it was that whatever area was larger than an absolute value, right, or greater than an absolute value. We went in that direction, and then multiplied it by 2 because we had two tails. We then compare our p-value to alpha, and if the p-value was less than alpha, we said we could reject. If it wasn't, we said we failed to reject. Okay. The critical value approach was very similar. First two steps, identical. It's the same thing. We then can do the next two in either order. I would probably put this one ahead of step. I would probably put step 4 ahead of step 3, but you could do it either way. Use alpha and the type of test to find our critical values. When we have our critical values, we then can determine where our rejection region is. We then find the test statistic and plot it against those critical values and see if it's in the rejection region at that level of alpha. And so that was kind of the fifth and final step. So you can calculate this first, then find the critical values, and then plot them. But I would always suggest plotting the critical values in the rejection region before you plot the test statistic. Okay? And we'll get a couple examples of this today. We can use either approach, and both will lead to the same decisions in terms of rejection. So what we're going to do to complicate what we did before is, instead of just one population, we're now going to be comparing two different populations. Right? So we're not going to have the population data, we're only going to have samples from each population. But the idea is we're sampling from two different populations. So the setup is going to be, we take two random samples, right? One random sample from one population, another random sample from another. Right? We're assuming that these populations are independent, random samples, so they are independent of each other. So we have independence across how we're sampling, so we make sure that we're not, let's say I was randomly sampling people from the U.S. and comparing them to people in Michigan. Well, I could get people from Michigan in either one, and so maybe I want to do everyone not in Michigan but in the rest of the U.S. and then everybody in Michigan or something like that, to make sure there's no overlap there. So then the sampling distribution, if we have this independence, we actually know, right? Well, at least we're not going to go through kind of the mathematical proof, so I guess you'll have to kind of trust me here. We could walk through a very similar thing like we did when I said you had to trust me and we walk through all the birth data. The same thing would be here. We could look at the mathematical proof, probably a little bit too complicated for this course, but we could probably prove it to ourselves pretty easily with data if we had two population data sets. So what's going to be true is the sampling distribution for the difference between these two sample means, right? We took two samples. If I look at the difference between those sample means, it should be Norman distributed as long as we meet that central limit theorem. Right? So as long as that central limit theorem is met, we know that the difference between those sample means should be Norman distributed. Not only is it going to be Norman distributed, we're going to know some other properties about it too, which we'll see here in just a second. So just like before, we not only can compare two sample means, we're going to have situations where we have two sample means, looking at the difference between them, and we have population variances, and one where we don't know the population variance, all we have is a sample variance. Just like before, when we know the population variance, the difference in sample means, we use the z, or standard normal distribution. When we don't know the population variance and only have the sample variance, that's where we use that student t. So the same kind of rules apply, it's just now we've got two means instead of one. And then if we're looking at the difference between two proportions, that's still going to be the z, or standard normal table, just like it was before. So anytime we see proportions, always go to that standard normal, or z table. So we can do confidence intervals, we can also do hypothesis testing for each of these three different situations, right? Same three types of tests, right, left, two-tailed tests, right, or greater than, less than, not equal to tests. So it's going to be very similar rules as what we did before. It's just our equations to find the confidence interval and our equations to find our test statistics are going to be a little different. But the process of hypothesis testing is the same. The only difference is our equation for the test statistic, and the process for confidence intervals is the same. It's just slightly different equations. Right? And then finally, which I don't think we'll get to this week, likely next week, we'll talk about match pairs. So really, we're going to try to get through 1 and 2 this week, and then situation 3, which is student T, and then also match pairs, we'll likely cover next week. So, kind of have 3 different motivating examples. One, we're going to be comparing the starting salary of econ and theater majors. We know the population variances, right? So we could build a confidence interval, we could do some hypothesis testing. The second one, I've got this 2011 Hoosier survey. It's in 2 different time periods. We're going to compare the proportion of people that were in favor of the Affordable Health Care Act in both of those 2 different years. All right, so we're going to be comparing proportions here. And then here, I've got drivers who are texting and not texting. And so I'm going to be comparing 2 different, where is it? Here we go. Sample means, but I only have sample variances here. So these are our 3 kind of examples that we'll run with. We'll do confidence intervals for them. We'll do some hypothesis testing. Right? So just kind of setting this up. So if we're comparing 2 population means, and we know the population variance, this was our first scenario. All right. So if that's the case, then we might switch here to the board in just a second. But oh, there we go. I want to make sure that everything's still running. Okay, everything's still running correctly. So we got our first population, which we look at. Here's my population mean. I don't know what it is, but it exists. There's some population variance, and we'll just notate that this is coming from the first population with a 1. We then take a sample of size n, right? If we do that, then n1 is our sample size from the first group, and we can calculate a sample mean for that first group. Right? We can then do the same exact thing for population 2, and we just put a subscript of 2 for that population's mean, variance, sample size, and sample mean. Okay. So once we draw those, right, we know that the mean for the difference in our sample means will be whatever the true difference is between the population means. So I'm going to draw a little bit here so we can kind of connect this with what we had been doing before. If I can get my marker cap off with one hand. There we go. So before, get this to autofocus. Oh no. Oh, what can? Let's see if I start drawing if it helps. No. Oh, come on, it was just working. Let's try switching. There we go. So before we were looking at a sample mean, we said it was centered around whatever the true population mean was, and the standard deviation of those sample means was the square root of the original population variance over our sample size. So what we're doing now is we're looking for the difference in means. So we can take these 2 sample means and we find the difference, right, or subtract the second one from the first one. Well, as long as the central limit theorem is met, the same sort of scenario applies where the distribution of that difference I could see, because I could see a whole bunch of different values for these sample means, I could see a whole bunch of different differences. But I know those differences will follow a normal distribution. And I'll try to give you a little bit of an idea visually of why that's the case in just a second. But for now, just trust me. It'll be normally distributed, and it will be normally distributed around whatever that true difference is. Right? So it's going to be distributed around whatever that true difference is. And now the standard deviation of the difference in those sample means, well, it's actually just going to be if we took the variance of each one of these, added them up, that's our variance for the difference in sample means. If we want the standard deviation, we take the square root. So the square root of the first sample means variance plus the second sample means variance. Right, this guy represents the first sample means variance. This is the second. If we want the variance of the difference in the 2, we would add them up. If we want the standard deviation, we'd add them up and take the square root. Okay? I'm going to stop here for a second. make sure I saw there's a few people watching. If there's any questions, I know there's a slight delay, so if you have any questions, can ask now. I'll pause this for a second before I erase this. So you can kind of see it's very similar to what we were doing before, just we have a different statistic now. It's not just a sample mean, it's a difference in two sample means, right? But notice, very similar. Instead of being centered around the population mean, it's centered around the difference in the population means. Instead of just being the variance for one sample, it's the add the variance of the two samples together, right? So are these questions or the test? So this is the next chapter, right? So this is, we're looking at two populations. We didn't do anything with comparing two different populations before. This kind of comes from the last exam, and so I'm comparing what we're now doing to what we had done before, right? Very similar ideas, it's just a little bit, right? Things get a little bit more complicated. There's just a few more moving parts, but the idea behind it is the exact same. Right? So yeah, this is kind of the next chapter. Okay. So why is this normally distributed? I want to try to give you somewhat of an idea as to why that's the case, right? So hopefully everyone's kind of got this written down. I'm gonna erase this here real quick. If not, you can always kind of go back and post this and make sure you have everything filled in correctly. So let's say I'm thinking about I have two distributions, right? So one, here's the distribution of my first population. Right? The sample means should be centered around whatever that true population mean is. Let's then say I've got another population that has a kind of higher value. Right? So what are going to be, what's the difference that I could see if I looked at the difference between the two that would be the most likely? Well, if these two values are the most likely for me to see, then whatever that difference is, that's going to be the most likely difference that I could see. So whatever that difference is, I could say, well, that's going to be, I can think about here now the difference between my sample means. This would be the most likely difference I could see because these two values would be the most likely I see from taking a random sample. So whatever that difference is, it's the most likely. Now if I think about, okay, what if I found something here and found something here? Not quite as likely, but pretty high. What's that difference? Well, it's probably a little bit lower, right? Because they're a little bit closer together. And I kind of keep going and everything becomes a little less likely. And then the same thing in the other direction. What if I see something here and something here? Well, they're still pretty likely. It's a larger difference. And then as I start to go out further to see those larger differences, it becomes less and less likely. So because we know that the distributions of each of our sample means start out as normal, we know that that difference between the two will also be normal. That might not be completely clear, but that is what's going on. And you don't have to have a perfect understanding of that to mechanically be able to work on these problems with two sample means, but this is kind of what's going on behind the scenes and why we know that the distribution of the difference in those sample means will be normally distributed. Okay? All right, so go back to the slides here. So I kind of drew this on the board there, but we know the mean of this difference will be whatever the true difference is, and that the standard deviation will be the square root of, take the variance from each population, divide it by its sample size, and then add those together. Okay? So we now know something about what the distribution looks like. Well, once we know it's normally distributed, we can do just the same thing we were doing before to build our confidence intervals. We don't know what this true difference is between the population means because we can't see the population means. But we can use our sample means to build a range of possible values that difference could be between. Okay? So, for building confidence intervals, just like before, it's going to look like a very similar equation. So, I'm going to once again try to make the comparison to what we were doing before with confidence intervals when we knew the population mean, and what we do now when we have two populations. So, go back here. Before, what we did was we took our sample mean, and we added to get the upper bound, subtracted to get the lower bound. We looked up the z value that gave us alpha over 2 on either side of our confidence interval. And then here, we were multiplying by the standard deviation of our sample means, which we knew was the square root of, so here, square root of the population variance over the sample size. So I should probably rewrite this so it's a little bit clearer on the screen. So this is what we were doing, but this guy right here we knew represented the standard deviation of our sample means. So it's going to be the exact same setup, we just have a different statistic. So we always, to get a confidence interval, take the test statistic you're interested in, add or subtract a certain number of standard deviations away that gives you your desired alpha over 2 in each tail. So this is alpha divided by 2. And then multiply it by the standard deviation of that test or of that statistic you're looking at. So what's the statistic we're interested in now? Well, it's going to be not the sample mean, but the difference in our sample means. Because we know the population variances, we'll still be using that standard normal or z distribution. I'm going to kind of run into myself here. And now I'll divide by the square root of each sample means population variance from which it was randomly sampled from, added together. So we've got the first and the second, right? First population's variance divided by the sample size I took from that population. Second population's variance divided by the sample size I took from that population. Now what does this represent? Well, this is not the standard deviation of our sample means anymore. This is the standard deviation of the difference in those sample means. So it's the same sort of setup, it's just, yeah, this standard deviation has a few more moving components than that standard deviation did. Right? But once I know all these parts, it's really just a matter of plugging them in. Plugging everything in that I know, and then looking up how many standard deviations away do I need to go to get that alpha over 2 on each side of my confidence interval. Okay? So hopefully that looks somewhat familiar from what we're doing before with confidence intervals. And yeah, you know, we've seen things that look like this before. So how do we solve? For the first thing we do, we just identify what we're given. We will always be given the sample means. We'll have to know the population variances or standard deviations. Right? If we know one, we know the other. And then our sample sizes. And then, of course, what level of alpha do we want to test against? We could always do multiple levels of alpha at the same time. I mean, we could build confidence intervals for different alphas if we wanted to, especially in Excel. Excuse me, just like we did for one population, and you had to hopefully do on your last Excel assignment, you could do that for 2 populations as well. And I'll show you a little bit of that probably today or I'll see if we do it today or tomorrow. So what is the next thing we have to do? What is the z value that we need? And then from there we have all the components, and it's just a matter of plugging into that equation, right? So we've got our lower bound equation, we got our upper bound equation. The lower bound we subtract what we said, there was that kind of margin of error. Upper bound, you add that same value. So same thing as before. Before we said the sample mean had to be smack dab in the middle of our confidence interval. Well, now the difference in our sample means has to be smack dab in the middle of our confidence interval. So let's go to this example. Right? Let's say we got 40 econ alum and 50 theater alum. The econ alum had a starting salary of $45,000. The theater alum had a starting salary of $33,000. Right? We then have the population variance for both of these groups, and we want to build the 95% confidence interval. Right? Well, what do we do first, right? Well, first of all, let's identify the 6 components that we need here. So we've got sample size from the first group is 40, sample size from the second group is 50, because here we define the difference between econ and theater, so we'll define econ alum as group 1. We've got the population variance for both groups, and we have the population mean for both groups. Sorry, not population mean. We have the sample mean from both groups. Okay. So we've got these 6 pieces of information. What's our alpha? Well, at the 95% confidence level, remember alpha is kind of the decimal or decimal version of the percent outside of interval. So there's 5% outside the confidence interval, which is an alpha of, in decimal form, 0.05. So 0.05 is our alpha. So we need to find the z-score that gives us half of that alpha on either side of the interval. So 0.05 over 2 is 0.025. So we look up that z value by going here to our z-tables. Let's zoom in so you can see these a little better. So we know the area we want on each side of an interval is 0.025, so I'm going to look up that area in the middle, right? These represent probabilities or the area in the tail. So I look up 0.025 because I know that's what I want. Here it is. The z-score that would give that to me is negative 1.96. Like we said, the positive and negative are kind of already built into our confidence interval. The negative gives us the lower bound, the positive, right, going 1.96 standard deviations below the sample difference we found gives us a lower bound. Going 1.96 standard deviations above would give us the upper bound at the 95% level. So we really just kind of talked through everything, but here it's kind of written down, right? We identify the 6 pieces of information that we need, and then the 7th is that alpha. We divide alpha by 2 to look up that z-score of 1.96, and from here, it's just, we've got our equations, right? It's just a matter of plugging in those components. We know everything now. It's just a matter of plugging and chugging. So we end up plugging everything in, and we find that the true difference in starting salary is somewhere between 11,960 and 12,000. Now, the reason why this is such a tight confidence interval here is I think is because I chose these variance numbers, and they probably should be a lot higher, but I wanted to make sure if you're working through this and trying to replicate this, that we didn't have these outrageously high numbers to deal with. It's probably more likely that these are actually like the standard deviations, in which case if they were only the standard deviation, when we plug them in, we'd have to square them, right? And would give us a much wider confidence interval. Okay? But regardless, here's our confidence interval. So with 95% confidence, I can say that the true difference between these 2 different major starting salaries is somewhere in this range, right? And the goal is to be able to say things with a high level of confidence, but for a narrow range of values. So for this one, it's pretty good. We can say with 95% confidence, it's in between these. So we've got a question. So how did I find that z-score? All right, so the first step was identifying our alpha, right? So the 95% level, what percent is outside the interval? So 95% is within, 5% is without. Okay? So our alpha is 0.05, right? That percentage in decimal form. We then need to find the z-score that gives us that alpha outside our interval, but there's 2 sides, right? There's a left side of our interval and a right side, right? We have a lower and upper bound. So half is on each side. So 0.05 divided by 2 is 0.025, right? So that's the area I want in my tail. So I go to my z-table and I say, look, I need to find the number of standard deviations away from the mean I need to go to get 0.025 in this tail, right? Remember, that's the interpretation of the z-score, the number of standard deviations away from the mean. So what z-score would give me 0.025 in that lower left tail, because the same z-score would also give me 0.025 in that right tail, or the left and right side of my confidence interval. So I look at 0.025. Let's see, the closest I can get, it's actually exactly 0.025 is right here. What z-score would give that area in the tail to me? Negative 1.96. Negative 1.96. Okay? So that's how I find that z value. Right. So it's kind of like when we did the inverse transformation. It's essentially the same process to find this z-score that gives you whatever desired alpha you want in the tail. Does it help answer the question the person asked? So there's a slight delay on this, so hopefully the answer is yes as I continue. But so we have that z value, yep. And once we have that, it's just a matter of plugging everything in, right? So I hope at that point it's not too bad. Okay. So this would be like I said, obviously we're not using iClickers, but this would be a good example of a question I could ask. And then also, like I mentioned, I'll leave the iClicker labels in the slides so that as you're going back, these are the ones that it's really good to make sure you know how to solve on your own. Okay? So you can see me work through it, but you can also work through it as well and make sure you can replicate. So let's say we've got, what, from 1982 to 2005, I've got robbery rates for Ohio and Indiana, right? I've got, for every year, I've got the rate. So I've got 24 years, so for each state, I've got 24 observations, or 24 years, which would be my kind of sample size, 24 for each. 24 of the possible, however many years that have existed for Indiana and Ohio being states. So I found the Indiana robbery rate was 109. I know the population variance somehow is 175. And in Ohio, I found the mean robbery rate is 163, but I know their population variance is much, much higher, right? So let's say I wanted to build a 95% confidence interval for the difference between Indiana and Ohio. So this is where it becomes important that we've got the ordering correct, right? Otherwise, we'll get everything but exactly the opposite, right? So here, I've got my mean rate for Indiana is 109. The mean rate for Ohio is 163. So the difference between those two is negative, right? Indiana is smaller than Ohio. So this difference is going to be a negative value. In fact, if we look here, it's going to be what, negative 54. So I know that my confidence interval should be centered around that difference. So it should be centered around negative 54. I would then add something to get my upper bound, subtract to get my lower bound. So I know that this has to be smack dab in the middle of my confidence interval. Right? Well, if I know the population variances, just like before, and I want to do the 95% confidence interval again, what's my alpha going to be? Still 0.05. So when I divide that by 2, it's still 0.025. So when I look 0.025 in the table, I'm still going to find 1.96. So we're using that standard normal distribution. It's really nice and easy because we're going to find the same values for these different levels of confidence every single time. When you want a 95% confidence interval and you have the population variances, you're always going to find that z-score of 1.96. If I want the 10% or the 90% confidence interval, so I've got an alpha of 0.1. Well, when I divide that by 2, it's 0.05. When I look at the table, it's about 1.65. It's always going to be that, right? So that's kind of nice when we're dealing with that standard normal because these values keep being the same, and we're looking at the same three levels of alpha, right? 0.01, 0.05, 0.1. It's a little bit harder when we have the student t-distribution, but for now, we're using the standard normal, so that makes it easier. And then it's just a matter of plugging in the other components that we know here to plug it, to get our final lower and upper bound. But just knowing it's centered around that, right, negative 54, right away we can rule out answer D, right? Because it's not even in the interval, right? I think for the other ones, it looks like it's kind of in the middle of most of these. Yeah, it looks like it's in the middle for the rest of these. But that's one way we can kind of rule out answers. So we know it can't be D here. And I would say on the exam, one mistake I saw was in a lot of these, like, I think the best way to do it is rule out which ones, and maybe because it's on a screen and you can't physically cross them, I don't know. But there's a lot of times where people even answer like the exact opposite, where it's like if you just stop and think about the principles right away, we can automatically eliminate this, right? I think the actual answer probably is A, but if you mixed up Indiana and Ohio, right, you would end up finding D, right? So we need to be a little bit careful about what we're doing. So we've got everything that we need. We talked about the z-score. It's the same way we found it before, so we don't even really have to go through that process again. And then it's just a matter of plugging everything in, right? So we get this range of possible values. So with 95% confidence, I could say that Indiana has lower robbery rates than Ohio, right? In fact, I can even say that with 95% confidence, the amount lower that they are is between 43 and 64 crimes lower. I think it was crimes per 100,000 people. Yeah, per 100,000 people, right? So that's kind of how we can interpret that confidence interval. With 95% confidence, I know the true difference has to be negative. So if that true difference is negative, I know that Indiana, right, is lower than Ohio. And with 95% confidence, I know how much lower. Well, between 43 and 64 lower. Okay. So another example of kind of how you build a confidence interval when you know the population variances. So what if we wanted to do hypothesis testing, right? So we're going to do this today for examples where we have two population means and we also have proportions. Okay. So the difference between these two means, right, we're just going to call this capital D, or this is the true difference. If we knew what the population means were, the difference between those would be kind of this capital D. Right? So now we're going to assume some value for what this difference is. We're going to assume that it's 0 or 50 or negative 10, whatever. Right? Well, the setup would be very similar. Now, often, and I say often actually in the exams, for these two population examples, I'll always give you this value to be 0. And we'll see why that kind of makes sense. But I'll also walk you through some examples where what if we wanted to do something other than 0? Because outside of this class, you may not always want to assume the difference is 0. So we've got 3 different propositions we could test. We could say, okay, is this true difference greater than this assumed value? Is it less than this assumed value, or is it not equal to? Same thing we had before. Greater than, because there's a greater than sign of the alternative hypothesis, so right tail. Less than test, less than sign of the alternative hypothesis, so left tail test. And then a not equals to sign, or a two-tailed test. All right? So one-sided, two-sided test, just like we had before. Nothing really has changed much here. But if we think about, okay, the steps to do this hypothesis test. Well, the first step is, and we reviewed this at the very beginning today. So I think this one, hopefully, I think I have it set up to do the p-value approach. But you determine the null and alternative hypothesis, right? It's a little bit trickier than it was before. This is also one on the exam. I'm not sure exactly. I didn't try to trick anyone. And whatever you want to test for, that's your alternative hypothesis. So if I say I want to test for whether or not something is less than a certain value, then the alternative hypothesis is a less than sign. Even the short answer, I had some people, the short answer was, is it different than this amount? Well, if you see that word different than, there should be what sign in the alternative hypothesis? A not equal to sign, right? You just want to know, is it different or is it not equal to this value? Okay? So now with a difference, it's going to be a little bit harder, and we'll see in the examples why step 1 is a little bit harder when we're looking at the difference in sample means. We still need to know what level of alpha we're testing against. Using the type of test in alpha, so here I have the critical value approach because we'll look up the critical value. I then calculate my test statistic, and then I compare and say, is my test statistic in those rejection regions given what my critical values were? Okay. I could do the p-value approach as well. Let me see if I can get these all to be uncovered here. I don't know why. There we go. So it's going to be the same exact thing as we did before. And what we're really trying to do is say, well, the p-value is the probability that I saw not a sample mean, but the difference in the sample means that I did if the assumed true difference was in fact true. Right? So if the assumed true difference is true, what's the probability, or the p-value is what's the probability I saw the sample difference that I did, or anything more extreme, right? Or anything more extreme or greater in absolute value. So if we had a right-tailed test, whenever we found that test statistic, we were looking for the area to the right. Left-tailed test, we were looking for the area to the left. Two-tailed test, well, it depended. If I found a test statistic that was positive, then I found the area to the right and multiplied it by 2. If I had a test statistic that was negative for a two-tailed test, I found the area to the left and multiplied it by 2. Right? So kind of visually, right, well, I think I have a two-tailed example here, so I'll be able to kind of show you this. Right? Well, the critical values are actually for these examples where we know the population variance are going to be the exact same thing we had when we had one population. Because it's the same 3 alpha values, we're using the same standard normal distribution, and so when I look up these different alpha values to be in one tail, right, so greater than they're in the right tail, less than they'd be in the left tail, I'll find the same values I did before, 1.282, 1.645, 2.326. For the right tail test, they're positive. For the left tail test, those critical values would be on the left side, so negative. Now for a two-tailed test, I don't look up an alpha of 0.1 because alpha is divided now into 2 tails. So now it looks more similar to like the confidence interval when we use the table. So there's half of alpha in each tail, so I would look up 0.05, 0.025, 0.005, and always find these same 3 values. Now for a two-tailed test though, there's a left and right tail, so it's critical values on either side, so I have pairs of critical values. A lot of you on the short answer, and I didn't take a lot of points off for this, but you found the right values maybe for that two-tailed test, but you forgot to identify that there's actually pairs of critical values at each alpha. Okay? And then here you can remember this, like less than, greater than, but the easiest way is if your test statistic is more extreme than your critical value, or larger in absolute value, right? Absolute value is when we kind of drop the signs, then you reject. If it's less than an absolute value or not as extreme as your critical value, then you would fail to reject. Okay? So what's the only thing that really changes from what we were doing before? And here, I'll come back to this, but this is going to be our new test statistical equation. And I mean, we could have almost maybe guessed it from what we did with the confidence intervals, that this test statistical equation was going to look the way it did. So before, when we had one sample mean, we took the sample mean that we saw, we subtracted the assumed true mean, and then we divided by the square root of the population variance over the sample size, where this denominator represented the standard deviation of our sample means. To get a z-score, we always take the statistic we're interested in, subtract the assumed true value, and divide by the standard deviation of that statistic. So if instead we want to find the test statistic for the difference in sample means, well, what statistic are we interested in? Not the sample mean anymore, but the difference in sample means. Well, we no longer have, what's the mean of this difference? Well, it's no longer just the one population mean. Now it's the assumed true difference, right? Instead of the assumed true mean, the assumed true difference. And remember, this kind of represented, we could write this as like my sample difference that I found. Let's see if I can get this to be a little bigger. There we go. And now I'll divide by the standard deviation of the difference in my sample means, which from doing the confidence intervals, we knew was the square root of each group's population variance over the sample size I took from that group, right? So it's very similar to what we were doing before. It's just now the standard deviation is a little more complicated. Instead of a sample mean, we're looking for the difference in sample means. But the process is really very, very much the same, okay? So that's the equation. I just want to kind of show you the analogy of what we had done before, but that's the equation that we have here in this slide, right? Trying to think, hopefully, yeah, where that difference in sample means we could think of as like the sample difference that we found between these two groups, okay? So what does an example look like, right? Basically, we're going to be doing hypothesis testing using this new equation for our test statistic. Whoops, well, I guess we already know the answer, but how do we get to that answer? So let's say I've got tropical storms from 1990 to 2011 and 1958 to 89, right? So I've got two different time periods. One I have 32 years, so a sample size of 32. The other I have a sample size of 22. Right? Well, if I somehow know the population variance over like the entire time period that we've been having tropical storm, let's say I know that somehow in those two time periods, what would be the null alternative hypothesis if I wanted to test for whether or not tropical storms have increased in recent years? So I want to think about, have they increased in recent years, right? What would I want to look at for the difference? Well, here I kind of let you know the newer time period is group 1 and the older time period is group 2. But anytime we have a timing example, you always want the newest year to be your group 1. Because when you're looking at the difference, you go new minus old, it just, the way we say it in English, it makes more sense, right? If I say that they've went up, right? If tropical storms have increased, then this difference should be positive because mean 1 would be greater than mean 2. If they've decreased, mean 1 would be less than mean 2. If I somehow flipped it around, well, now if storms have increased, and I had these two flipped, now this number would be negative, which doesn't like really make a whole lot of sense. So we always, it's just easier if we make that group 1 the newest time period, right? The way in which we would say it in English. So I've got my groups identified. If I want to know whether or not tropical storms have increased, then that means that this difference, if the newer time period is group 1, this difference should be positive. So that's what I want to test for. So my alternative hypothesis is what I want to test for, is that this difference, right, is greater than 0 or positive, okay? Now for every example that I'll give you for the exam, like any example I could use in the exam, I'm always going to use this assumed true difference as 0. And you can kind of see why now here, because it has a really nice interpretation. Has this difference, right, has it went up, has it went down, right? Is the difference positive or is it negative? Or if is it 0, has it changed at all, right? Now, if I start to put in numbers like, is it greater than 9.7? Well, now the interpretation would be, have tropical storms increased by more than 9.7 storms a year? Here we just want to know, has it increased at all? Here, has it increased by more than 9.7? So we can still do that. It's just more of the questions that we're actually asking are likely going to have this as 0 as the assumed true difference. Right? So what type of tail test would we have? Well, we go to the alternative hypothesis. What's our sign? So greater than sign. So a right-tailed test. Okay. So what should my critical value be at the 5% level? Well, right away, I should be able to rule out some of these answers. If it's a right-tailed test, I'm looking for a value on the right side of my distribution. So automatically, I know it has to be positive, right? Because when I say the right side of my distribution, well, if I know the population variances, I'm using the standard normal or z-tables. So if I'm using the standard normal or z-tables and I have a right-tailed test, what do I know the mean of the z distribution is, or standard normal distribution, is 0. So if I'm on the right side, my critical values would be positive. If I was on the left side, my critical values would be negative. So I want to find the z value, or the critical value, that gives me alpha in the tail. I believe I said I wanted 0.05 in the tail. So I can do this 2 ways, right? Actually, sorry, I can do this 3 ways, right? So I'll show you all 3 on the screen here. So I want 0.05 in that upper right tail. So the first way is I go to my z-table. Well, I want 0.05 in the upper right tail, and I know that my critical value would be positive. Well, because it's a symmetric distribution, the area to the right of that positive z-score will be the same as the area to the left of the negative of that z-score. So if I look up the area of 0.05, so I say, okay, where's 0.05? Looks like it's in between these 2 values. So negative 1.64 and negative 1.65, it's in between those 2. I'll take the higher of the 2, so about negative 1.65. But it was a right-tailed test, so I knew it was that value, but positive. Now I could have also said, well, if there's 0.05 in the upper right tail, that means there would be 0.95 below it. So I could have also looked up the probability of 0.95. It's in between these 2. So 1.64 and 1.65. Take the higher of the 2, 1.65. Got me the same answer. Now I think this is the easier way, but you technically are using a different table. But we said on the student t-tables, the last row represented the values you would find from the standard normal table, right? Because if we had degrees of freedom infinity, essentially the student t becomes the standard normal. So now I could just look up, well, I wanted 0.1, 0.05, and 0.01 in my tail. So I go down here. I could look up the critical value for any one of those levels. I believe what we wanted was 0.05, and I could get it even more exact. So not 1.65, but 1.645. Okay. So 3 ways of finding the same value. Finding out the third decimal using that student t-table would kind of be like I said, probably the best way to start doing that, and the easiest way. It saves you the most time. Okay. Unless you have a weird alpha. Unless you have like an alpha of like 0.04, 0.08 or something like that. But I'm not asking you to do those. So for the sake of what we're doing, that won't be an issue. Okay. What will my test statistic be? I mean, these test statistic ones should be easy, and as long as you can identify what equation you need to use, they should just be plugging value. They're just plugging numbers in, right? So I've got my 2 sample means, I have my 2 population variances, and I have my 2 sample sizes. That's all I need. The only other thing I need is what's my assumed true difference. Well, I said for the examples we're going to use, the assumed true difference is always, we use this cutoff from the null and alternative hypothesis of 0. So if I go to my test statistic equation, I plug in everything I know, the assumed true difference is 0. Really I can ignore this assumed true difference. If I'm telling you it's always going to be, is it greater than, less than, or not equal to 0, subtracting 0 doesn't change anything. Right? So what does this test statistic kind of reflect? Right? Well, we were assuming that the difference between these 2 time periods was 0. Right? In fact, we were assuming that the true difference was less than or equal to 0. Well, we found pretty strong evidence, right, that there is a difference. In fact, it is positive that they have increased. How many standard deviations away from 0, though, is that difference? Well, that's what our test statistic tells us. The test statistic here is still a z-value, so it's now the number of standard deviations away from, not the true difference, but the assumed true difference. So if in fact the assumed true difference of 0 is correct, the evidence we found from our samples is 4.9 standard deviations away from that. Really, anything more than 2 standard deviations is pretty far. So at 4.9, we're very far away from that assumed true difference. So it would be very unlikely that, given the sample evidence we found, that this actually is the assumed true difference. It's probably that the true difference is not 0, but something closer to, 5 or 6, right? Whatever that difference is we found. Okay. So if I wanted to make my rejection decision here, how would I do that? Well, I had my critical value, which was 1.645. So I've got 1.645. Where does my test statistic of 4.9 fall? Way over here. All right. And so this is my rejection region. My test statistic here is clearly in the rejection region. Sorry, I don't know if you can see that. Here's my rejection region. Clearly it's in the rejection region. So we reject, and remember this corresponds to an alpha of 0.05 or at the 95% confidence level. Right. This is not a 6. Hold on. I'll write this a little bit better. There we go. Right. Now what if I had found a test statistic of 1.3? Well, then it would be over here. And I would not be in the rejection region, so I would fail to reject, right? But given the test statistic that we found, we should reject. If we had found a smaller, then we would have failed to reject, okay? What would the p-value be approximately if we found this test statistic? Well, the p-value would be the probability I saw something this many standard deviations away from the assumed true difference or any further. So like the area to the right of my test statistic. So when I go to the table to look that up, all right, go to my z table, I'm thinking about, well, I know the area, I want to find the area to the right of 4.9. So the table always tells me the area to the left, so I can find the area to the left, subtract it from one of the area to the right. So I've got 4.9 as the z value that I found. Well, the table only goes up to 3.99. The area to the left of 3.99 is 1, right? So I'll try to give you a visual of this, right? The area to the left, so if I kind of draw another thing here, of 3.9, this area is approximately 1, which means the area to the right of that would be approximately 0. Well, I wanted the area to the right of, 4.9. So if the area to the right of 3.99 is basically 0, the area to the right of 4.9 is going to be even closer to 0. Right? So I know my p-value here is pretty much 0, which I reject if the p-value is less than alpha. Right? Well, if my p-value is pretty much 0, it's definitely going to be less than an alpha of 0.05. So I would for sure reject in this scenario as well. So both approaches led me to rejection decisions. Okay. So both approaches lead to the same rejection decisions. I'm trying to think what I want to do here. I think we'll kind of work through some more material. And then maybe I'll do more Excel tomorrow, right? And get that next Excel. Won't be posted yet, but once we go over it tomorrow, I'll get that posted. So let's compare two population proportions, right? It's going to be very similar to what we just walked through and did. We can do confidence intervals and hypothesis testing. So if we took a sample from one population, we know that with sample size n1 and the sample proportion we found, the best approximation we can get for the variance is going to be this guy right here. Same thing for the second sample. I took it from a different population, right? This is the best estimate we can get for the variance on that population as well. So we have to make sure these conditions are met. Which I said, I'm never going to give you examples where they're not and or try to trick you. But if we're going to be kind of complete with our setup, these things should hold. What ends up being true is, just like the difference in sample means, the difference in our sample proportions will be normally distributed. So they'll be normally distributed and centered around or have a mean of whatever the true difference is between those population proportions. Now all we have are samples, right? So we're looking at the distribution of these difference in sample proportions, but they should be centered around whatever the true difference in population proportions are. And here's kind of our equation for what the standard deviation should be. Now, if we don't know these, then we have to use our best estimates, which are use our sample proportion from group 1 and our sample proportion from group 2, because we don't, the whole point of us building a confidence interval or doing hypothesis testing is we don't know what these true population proportions are. Okay? So we're going to end up with a confidence interval equation that looks like this. So once again, I'll return to this, but I want to make the comparison to what we were just doing earlier. All right? So before, when we were looking at the comparison of two sample means where we knew the population variances, we had take the statistic you're interested in, add and subtract to it. Well, if you know the population variance, you get to use that z distribution. So the number of standard deviations away from what you found, from the sample difference you found, that you want to go to the left and the right. And here it was each group's sample mean variance. So the sample mean variance from each of these, add them up, take the square root. So this gave us the square root of, sorry, not the square root, the standard deviation of the difference in our sample means. But really that's because this represented the variance of my first group, this was the variance of my second group's sample means. So now we want to find the difference in sample proportions. So that's the statistic we're interested in, so we build our confidence interval around that. We still get to use this z, or standard normal distribution, because just like with one population, if we're looking at proportions, we know that they'll be distributed kind of normally with that standard normal distribution once we convert them, right, into test statistics or these z scores, not t scores. Now, really here what we want is then multiply by whatever the standard deviation of the statistic you're interested in is. So here it should be the difference in our sample proportions, that standard deviation, right? Well, what's that going to be? Well, it's going to be take the variance of each of these sample proportions, add them up, just like we did before, and take the square root. So now, instead of having a population variance, we know that for that first sample proportion, the variance will actually follow this. And then it's for our sample portion, so we divide by the sample size we're taking, and then we would have the same thing, but for the second group. As well. Right? So it's a very similar, it's the same kind of setup, it's just it looks a little bit more complicated. And this is when we're dealing with proportions. Right? So I've got this equation on the slides, but I just wanted to kind of show you where that comes from. Okay? So really, everything's the same as what we did before. It's just instead we have a different confidence interval equation. That's slightly different, right? So we still identify the pieces we need. Now it's actually even fewer pieces. There's only 4 and alpha. Once we have alpha, divide it by 2 and look up the z-score. So it's the exact same process to find that z-score for our confidence interval. And that's just a matter of plugging everything in. To get our lower bound, we subtract that margin of error. To get our upper bound, we add that margin of error. Okay? I'll kind of pause here and see if there's anyone, a couple people watching, if there's any questions at this point. Got a couple viewers, but all right. Okay. So wait for the delay, and then we'll kind of keep going if there's no questions. Okay. So, what was our motivating example for this one? Well, that was where we were going to look at the 2 different years and think about what was how favorable or unfavorable were the views of the Affordable Health Care Act in 2011 versus 2010. So let's say we want to build a 99% confidence interval for the difference between 2011 and 2010. Right? And then I have this little meme. I haven't had as many memes, so I'll have to start getting a few more in there. Right? Well, what are the pieces of information we need? Right? Well, the first is what's our group 1 and our group 2 going to be? Well, I already said before what the sample means, and the same thing applies to the sample proportions. What we want to do is use for group 1 the newest time period. So we'll use 2011. That'll be our group 1. So our sample proportion from group 1 was 0.51. The sample size was 607. The sample proportion for 2010 was 0.48, and the sample size was 600. So we've identified those. What's our alpha? Well, at the 99% confidence interval, alpha should be, right, the decimal form, whatever percent is outside the interval. So if there's 99% within, there's 1% outside, or 0.01. Right? So we've got all the information we need. The next thing is, how do I find this z-value that gives me alpha over 2 on each side of my confidence interval? Well, if the alpha is 0.01, when I divide it by 2, it's 0.005. So I go to the z-tables. I know the area I want in my tail is 0.005, and I want to know, okay, what z-score would give me that area in the tail. Right? So I have the area in the tail, or the probability, I know it, so I look up the probability in the middle here. So 0.005 looks like in between these two guys right here. So negative 2.57 and negative 2.58. I'll take the higher of the two. Negative 2.58. Oops. I kind of remember that positive and negative are already built into the confidence interval. I go negative 2.58 below to find the lower bound, positive 2.58 above to find the upper bound. So I've got that 2.58. I could be a little bit more exact. So how did I get that to the third decimal? Well, that was where I said the other way we could do this is, if I know I want 0.005 in that tail, 0.005 in that tail, I could use the student t table and use that last row where degrees of freedom is infinity, and I know the student t distribution is the standard normal, and get that 2.576. But like on an exam or something, I would, I'll round this to the second decimal, so that way no matter which way you use, you'll get the correct answer. Okay, so we have that z value now. It's just a matter of plugging things in. Right? And this, I thought I changed this to so it didn't run off the screen last night, but apparently I didn't save it. Right, just plug in kind of for the first sample I took, second sample. Now if I look at this difference, right, it's 0.03. My confidence interval should be centered around 0.03. Sure enough, it is. And like this one is interesting is if I wanted to say, well, look, over the last year, this Affordable Health Care Act, and not the current year, but if I wanted to say this back in 2011, I could say, well, look, the true difference with 99% confidence, I know that the views on this Affordable Health Care Act, well, they could have become more unfavorable, right? Because the percent was the percent that said it was unfavorable. Because there are positive values here that the difference could be positive, but it could be less unfavorable because that true difference could also be negative. In fact, one of the possibilities could be that views haven't changed at all, in which case, if views haven't changed at all, then the difference could actually be 0. So anytime your confidence interval includes that 0, we know we don't have a lot of power to say much. Because in fact, this could have become more unfavorable, less unfavorable, or the views might not have changed at all. Right? So this one, it's kind of hard to make any suggestions because we don't know even the direction, right? Now it would be much nicer if these were all positive values. So let's say instead the confidence interval was 0.04 to 0.1, which doesn't make sense for the numbers we have here, but just for a second. If it was 0.04 positive to 0.1, then with 99% confidence we could say that the difference is positive, or that the percent of unfavorable views in 2011 was greater than, and then we could actually say, well, yeah, it's become more unfavorable. But that's only if it only included positive values. Okay. All right, so we'll work through another example. So let's say that same survey found that 84% of people favored healthcare coverage for everyone, and in 2010, only 82% of people supported that. So what would the 99% confidence interval be for the difference between 2011 and 2010? Well, first of all, we're going to do the same exact thing. So we go back to the equation that we're using. Oops. Okay. It's going to be centered around whatever that difference is. Well, in the current year, it said 84% of people supported healthcare coverage for everyone, so 0.84. The year prior, it was 0.82. So we found a positive difference of 0.02. So our confidence interval should be centered around that. Right? When it comes to looking up that z-value, we'll notice if we want the 99, we had the 99% interval in the example we looked at before. If I still want the 99% interval, right, my alpha is still going to be 0.01. When I divide it by 2, it's still going to be 0.005. So when I look it up in the tables, I'm still going to find the same value of 2.576, or approximately 2.58. So really, I don't have to look it up again because I just looked it up for the previous example. I know that it should be centered around that difference between the two, so 0.02 is the difference. So here I look, okay, which of the, well, this one doesn't even include 0.02. I can throw that one out right away. It looks like the rest of these are centered around 0.02, so we can't rule out A, B, or D. But we could rule out C there because 0.02, the sample difference we found, should be in the middle of the interval, and it's not even in the interval in this one. Right? So from here, it's just a matter of plugging values in. We've got sample sizes from both groups, our sample proportions. We got that alpha of 0.01. We said, okay, we're going to find the same z-value we did before. If we're using that standard normal table, when we look up these alpha values, we're always going to find the same z-values that give us that desired alpha over 2 on each side of our confidence interval. From here, it's just a matter of plugging things in, subtracting that margin of error to get the lower bound, adding it to get the upper bound. Okay? So with 99% confidence, I can't say whether or not people are more or less supportive of healthcare coverage for everyone, because the true difference could be positive, it could be negative, or it could even be that it hasn't changed at all, or the difference is 0. Right? All those possible values are in our range of our confidence interval. I want to keep doing some hypothesis testing, and we'll end after we do the hypothesis testing for proportions. And I think what we'll do is I'll then go over some Excel stuff tomorrow, and we'll start looking at differences in sample means when we only have, when we only have sample variances. Okay, and we'll kind of complete up a bunch of Excel stuff tomorrow. So we're going to revisit these examples in Excel tomorrow, but today we're going to set up how do we do the material. So one thing I do want to point out before we go on here, so I thought this was pretty interesting from this survey, some of the results that happened. Notice, okay, with levels of confidence, we can't say that the difference between these two time periods has changed, but one thing that is, one thing that's interesting is if you look at just like the percent of people in both years that favored healthcare coverage for everyone, it was like 84%, which is like one of the main components of the Affordable Health Care Act, right? But only about 50% of people supported that. So it's maybe one of these things where there were other parts of the Affordable Health Care Act that people maybe didn't like, but it is interesting that if you're thinking about policy and you look at these results, you're like, well, look, only about half of people really like this act, but man, about 80% of people, can really get behind healthcare coverage for everyone. So maybe let's change the policy a little bit to really focus on this, because we can for sure get this passed through, right? Most of the people want this. So I don't know, kind of an interesting way to start thinking about policy. All right. So we worked through this example. So let's do some hypothesis testing. So, whoops. There we go. Gosh bless it. All right. So, same kind of setup we had before. We're taking two samples. The only thing that's going to change for hypothesis testing, that when we're looking at the difference between two sample proportions instead of the difference between two sample means, is our test statistical equation becomes a little bit more complicated. Okay. If we don't have samples of the same size, then the distribution, right? The distribution of the difference in our sample proportions will, the standard deviation on that difference will not simply be kind of adding up these two variances, right? You kind of think about this as, because our sample proportions are impacted by the sample size, if we have differences in sample sizes and we're using the sample portion to be our estimate of the population portion, it won't work out to be exactly just adding these up. And so another way we can do this, and also kind of a nice way to do this, is an intermediate step where we rewrite this denominator so that we first calculate this thing we'll call P bar. Okay? P bar is just an intermediate calculation that will then plug in the denominator so that we can kind of all be working kind of on the same foot. So the way that we'll do these, like on the test, this P bar, you'll always round to kind of the second decimal. Right? So you'll round that to the second decimal, plug that in here, plug in your sample sizes, your sample proportions. It's kind of like one more step to calculate the test statistic, but it makes it a little bit easier, a lot fewer calculator mistakes if we do it this way. Okay? We're always going to do the same thing as we were before. That assumed true difference will always test against that value of 0. So is it greater than, less than, or not equal to 0? And the only step that changes is our test statistic equation is a little bit different. But once we plug the values in, it's very similar. Right? So here's our steps. I won't walk through them all. It's the same thing we had before. Literally the same steps as when we had two sample means. It's just now our test statistic equation becomes a little more complicated. So the process of these hypothesis tests don't change at all. So let's do this first one. So let's say we built the confidence interval already. And so I'll try to make a connection of the confidence interval and hypothesis test here. So let's say I've got that same setup, but instead of building a confidence interval, I want to test for whether or not Hoosiers have different views about universal health care coverage in 2010 and 2011. So what would my null alternative hypothesis be? Well, my group 1 is 2011, my group 2 is 2010, right? So we always take the newer years for group 1. Okay? So we'll take the difference between 2011 and 2010 proportions. Is that difference, well, if these two things were different, I can kind of show you on the board here real quick. If I just want to know, are the views different in those two time periods, then really what I'm saying is the sample proportion in 2011 not equal to the sample proportion in 2010? But if I write my null and alternative hypothesis out in the terms of this difference, well, how could I do that? What I'm really saying is if I just subtract from both sides 2010's sample proportion, then what I would end up with is this difference, not equal to 0. Okay? If they're not equal to each other, then the difference would have to be different than 0, right? If they're not the same value, it's something other than 0. So when we say that different than, still two-tailed test, not equal to sign the alternative hypothesis. Okay? So we've got a not equal to sign the alternative hypothesis, and I've already told you a couple times now, for these differences, I'm always going to use the assumed true difference of 0, right? Is it just different than? Different than each other would mean is that difference any value other than 0? So with this so let's say we do this interpretation. This would be, is the difference between 2011 and 2010 something other than 0.02? Is the difference something other than 0.82? But here we just want to know, are they different from each other? So is that difference anything other than 0? Okay? So that's our null alternative hypothesis, and it's a keyword is different than. So when you're doing that midterm kind of extra credit assignment, think about that as well. So not equal to 0, and if we have a not equal to sign in the alternative hypothesis, this should be a two-tailed test. So we got a two-tailed test. So what would the critical value be for this two-tailed test at the 1% level? Well, we're dealing with proportions, so we know we can use that standard norm or that z-table. Right? If we have a two-tailed test, alpha is getting divided up into two tails. Right? That's kind of maybe not completely self-explanatory, but two-tailed test, we've got two tails. Alpha is the total area in R. I think the way I wrote it once before was alpha, you can think about is the area in your tail, or if you have tails, it's the area in your tails. I'm going to scoot this over here. There we go. So we're dealing with that standard normal or z table because we're looking at proportions, right? Just like with one sample proportions, when we have two sample proportions, we still can use that standard normal distribution. Okay. if we've got two tails, then what we want to find is, okay, what is the pair of critical values, same value, but one's negative, one's positive, that gives us alpha total in the tails, which means that they're equally sized tails, so alpha over 2 is in each tail. So here I think I said it was the 99% level, so alpha would be 0.01, 99% level. So there's 0.005 in each tail. How can I find what that critical value is? I go to my two different ways. I can go to my z-table. I can find the area of 0.005, so looks like it's in between these two. Negative 2.57, negative 2.58, so the critical value, right, we have pairs for a two-tailed test, so it would be positive and negative 2.58 here. Or I could use that last row of the student t distribution, because I know that at degrees of freedom infinity, this is the same thing as a standard normal. I want a 0.005 in the tail. So this last column, positive and negative 2.576. Okay? Using that last row in the student t-table. So either way, it gets me the same answer, this positive and negative 2.576, or approximately positive and negative 2.58. Okay? So I've got my critical values. What's my test statistic? Okay. Well, if I think about it, if I'm looking at this, remember the test statistic is still a z-value. So the interpretation is still the number of standard deviations away, now not from the true difference, but from the assumed true difference. Well, the assumed true difference we had was, if we go back to the null hypothesis, the assumed true difference is 0. We found a difference of 0.02. That doesn't seem very far away from that difference of 0. However, when we take really high sample sizes, you know, our distribution narrows quite a bit. If you think about, let me see this test, there we go. If you think about this test statistic, as I have kind of higher sample sizes, these denominators get large, so this gets really small. Even a small difference of 0.02 could be a significant number of standard deviations away, right? The difference of 0.02 could be a significant number of standard deviations away from the assumed true difference of 0 with these really high sample sizes. Now, it's really hard to envision exactly where that test statistic is going to be until we plug everything in. But right, if I plug in the values here, and I'll repost the slides and plug these in here. This sample portion should be 0.84. This one should be 0.82. You're right, you should plug the values in here. If you do, you'll get 0.83. Now that you have 0.83, plug that into your p-bar, plug in everything else. The assumed true difference here is 0. So we do have about a test statistic of 0.92, or if the assumed true difference of 0 was correct, the sample evidence we found was about 0.92 standard deviations away from that. So it's not very far. In fact, we can kind of think about, given my test statistic at the 90% level, can I reject or fail to reject? Well, we found our, hold on, let's use a different color here. So we found our critical values were what? 2.58 and negative 2.58. So where would our test statistic of 0.92 be? Somewhere like right here. So here's our rejection region. We're not even close to that rejection region. So we fail to reject, right? Now, that's using the critical value approach. I could have used the p-value approach, which the p-value is, what's the probability I saw the sample difference I did that was 0.92 standard deviations away from the assumed true difference, or something even further away, right? Now, for a two-tailed test, anything I saw that was 0.92 standard deviations above that assumed true difference, it was equally as likely I saw something that was negative 0.92 or 0.92 standard deviations below that. So for a two-tailed test, my p-value, I'll take my test statistic. If my test statistic's positive, I find the area to the right and then multiply it by 2. If for some reason I found the test statistic and it was negative, well, for a two-tailed test, then I would look at the area to the left and multiply it by 2. Okay? But for here, we found the positive, so I'll find this area, multiply it by 2. I can look up 0.92, approximately 0.925, so we'll use 0.93 if we round that. So 0.93 in the z table. That's my test statistic. So I go down here. I can do this two ways, right? I can look up 0.93. The area to the left is 0.8238. Well, remember, 0.8238. So that's the area to the left. I want the area to the right. So 1 minus 0.8238. It's what? 0.1762, looks like. But remember, that's only half my p-value. I then have to multiply that by 2. So my p-value, right, because if this is 0.1762, this is as well. So I'll multiply that by 2. So my p-value is actually 0.1762 times 2. Or approximately, I'm not going to do the math, exact math, so 0.35-ish. Well, the p-value of 0.35, we only reject if the p-value is less than alpha. Is this going to be less than an alpha of 0.01 for the 99% level? No, so I would fail to reject here as well. Now I could have also, like, even though this is my test statistic, since I know this is symmetric, I could have looked up negative 0.92. If I did that, so negative 0.92, I would have found, oh, it looks like I did not, oh no, sorry, it was 0.93. 0.1762. So I could have done it either way, multiply that by 2. Either way would have got me to that correct p-value. Okay? So whether or not I do the critical value approach or the p-value approach, would have led me to the same rejection decision there. Okay? So that's kind of the new material for today. We're looking at the difference between two population sample means when we know the population variance, and the difference between two samples or two populations sample proportions. Both scenarios we use the standard normal or z-table. We can do confidence intervals or hypothesis testing. It doesn't look a whole lot different than what we're doing with one population, but right, our test statistic equation becomes a little more complicated in both scenarios. But it's not anything too crazy, and especially if we use these assumed true differences of 0, it makes the test statistic equations a little bit easier. One thing a lot of you did on the exam was you would flip the sample mean with the assumed true mean. So you would get the right test statistic, but it'd be negative instead of positive. At least that's what I noticed in the short answer. You could kind of see more of your work. So tomorrow, what we'll do is I think what I'm going to do tomorrow is I'm going to start out. I'm going to have to repost some more slides. We're going to start out looking at two population, and we're looking at the differences in means. So we have sample means, but we know only the sample variances. So then we have to go back to using the student t. So I'll walk through confidence interval and hypothesis testing for those examples, and then I'll probably stop. It'll be a short lecture, but then I'll continue. The stream will be longer, and then I'll do another separate video where I just work through the Excel stuff for two populations. Okay, so I'll work on we'll do that tomorrow. Like I said, watching these lectures is going to be really helpful because for that midterm extra credit assignment, really, yes, it's a little bit more complicated, but the concepts of how you do the confidence intervals and how you do the hypothesis testing, we're just working through more examples today and then also tomorrow as well. So I highly suggest, if you can, kind of tune in live for those, or try to make sure you watch the YouTube video, because that will help you get as many points possible on that extra credit assignment. Right, and so that extra credit assignment should be, let me double check, it should be up there on Canvas for both sections. If you have the document, you just upload kind of your work. I would suggest writing out as much as you possibly can. Most of you did a pretty good job in the short answer of the exam in terms of writing out a lot, so I could give a lot of partial credit. So a couple of you didn't, and if you got it wrong and you didn't show me any work, I really don't, it's hard to get partial credit. So put as much work as you want to into these, so I can give as much partial. I want to give as close to 15 points to everyone as possible, right? So please, all of you, do that before the end of the day, Friday this week. And other than that, that'll be the end for today's lecture. We'll have another one at 10:30 again tomorrow.